So today we're going to talk about regression and median fit lines. We're going to take those skills we worked on with scatter plots and lines of fit, and now we're going to practice writing equations. So to do that, we're working on the same skill as yesterday, SID 6, where we're representing data on quantitative variables with a scatter plot and describing how they're related. But we're also going to compute and interpret the correlation coefficient of a linear fit. So to do that, we have a bunch of vocab terms to talk about. The first one is a best fit line, and we've talked about this a little bit. The best fit line is the line that most closely approximates the data in a scatter plot. And for our purposes, we're going to be talking about a linear regression. A regression is the line of fit, and we're talking about linear functions. The correlation coefficient is a calculation of the strength of the association between the variables in the scatter plot. It's strongest when the absolute value of the correlation coefficient is closest to 1. So it can range from -1 to +1. Values that are close to 1 or -1 would be a strong association, and that's where we'd see those dots are close to a linear pattern. If it's near 0, then it's going to have if it's about a half, then we'd have a weak association. But if it's closer to 0, that tells us that there is a very weak or no association between our variables. That would be that idea of no correlation. A residual is the difference between the observed value of the dependent variable and the predicted value, and we can calculate a residual for each data point that we have. If we have a strong correlation coefficient, our residuals are going to be low. If we have a weak association, we're going to have some larger values for our residual. And there's other statistical analysis we can do with the residual value, but for today, we're just going to be calculating it. We also have the idea of causation. Causation can only be determined from an appropriately designed experiment. Our correlation, even if we have a super strong correlation, that doesn't mean we have causation. Causation tells us that the independent variable caused the change in the dependent variable, whereas correlation just shows us that they are related strongly. The last vocab term for today is a median fit line, which is a type of line of fit calculated using the medians of the coordinates of the data points. And so we're going to practice these fit lines using Desmos, using a graphing calculator. Here's some examples of some correlation coefficients, just so that you can see what I mean by a weak or a strong association. So this one here, this R value of 0.169, well, if I look at the data, there's no pattern. This is a very weak or a no. For my strength, there's no strength of correlation here. Whereas this one, with an R value, a correlation coefficient of 0.97, that's a pretty strong correlation. It definitely follows that linear pattern. This one here, -0.7, I can tell that there's a negative association, but those values are much farther away. This dot here is really far from the line. This one here is pretty far. There's a pattern, but it's not as strong. So this one would be a weak association. Or weaker at least. All of these have varying degrees. This one here, an R value of -0.094, well, there's no real association in the data here. This R value tells me that mathematically I would have a negative slope, but I don't see any sort of pattern. Whereas this one here, I have a very, very strong, I have an R value of -1. Those are linear, and if I were graphing this accurately, I should have scooched it down just a touch so it goes through each of those points. But this one here is a super strong association. Again, this last one, I see a pattern, but the association is not as strong as it is in either of these ones here. So these ones would be strong association, these ones would be weak association, these ones would be no real strength of my correlation coefficient. So to practice with this today, we're going to do an activity on Desmos. So if you open up Teams, you should see that worksheet, the PDF of the worksheet, and this is the top part of it. The first thing you need to do is, if you have not yet created your account on Desmos, you need to create your account. To do that, you'll go to student.desmos.com and type in our class code, which is RVA527, and it'll tell you welcome, and then it'll ask you to log in, but you'll need to click create account. You'll use your school email address, the first initial last name at helenastudent.org, and then I want you to set your password as your student ID number. That way, if you forget, I can help you. Once you've done that, you're going to go back to student.desmos.com and log in, and you're going to open up this activity, line of best fit. You're going to complete your work in the application inside that browser window and click submit. But I'm going to try to make a little video here that'll link to this so I can show you what you're going to be doing with that Desmos activity. So once you're logged into your account, you should see something that looks like this page here. It'll have the top two. That pumpkin carving bonus is still open until Friday this week if you'd like to keep working on it. But let's take a look at this line of best fit activity. Take a look at your instruction page here. You are going to do step 1, which is to go to the line of best fit. So when this page opens here, it's going to ask us, in our head, draw a line through the green points that fits them best. Which of the purple points does that intersect? Well, if I look at this here, I'm just going to take a straight edge here, a note card, and I'm going to try to figure out if I'm drawing my line of best fit using my skills from last year, I'm going to estimate that I think it's going to go through B. We'll use that as our estimation. And then in the box, you're going to explain your thinking. Well, my thinking on this one is when I put my line up to the page, it looked like about half the points were above and about half the points were below, and it followed the pattern of the data. So what you'll do is you'll type into that box and click Share with Class. I think as you do that you'll start to see responses from other students at the bottom of the page. Once you've done that, you'll click Next. Well, imagine in your head the line continuing out to x equals 100. How high do you think the line will be at that point? Well, if I take my line again and I look at it here, it went through B, which is at 15.5, but I need to continue that pattern out to where x equals 100. So my imaginary line started at 0, at the y-intercept of 0, which tells me that for every time I went up 5, I went over 15. Well, now I want to know if I go over 100. So I had 5 over 15 for my slope, but I want to know what is my value going to be when x is 100. Well, I can use my quick equation solving skills here, multiply both sides by 100, and I get 500 over 15. So that tells me that the line will be at about 33. So when I submit this, I think it's going to make me explain. Yep, I'll explain my thinking. And again, when you share your thoughts, you can tell me what you did. If you used a ratio, an equivalent ratio, if you used a linear equation, whatever you did to find a value, you'll share it with the class. Well then, now which line? Drag the movable points to create the line of best fit you were imagining. So the imaginary line that I drew in my head went through B, so I'm going to drag one dot onto B, and it went through the y-intercept. Looked something like this. I think that's all I do on this page. Then I click Next. Well, now here's the line that I created in the previous screen. How did I decide on that? Well, what I did is I was thinking about that idea of half above and half below and following the pattern. Why did I choose to go through 0, 0? I don't know. I chose to go through 0, 0 because often when we're estimating things, we go through 0, 0. Lots of times in real world situations, our x and y will be 0. Like on day 0, there were 0 cases of COVID. So I would have to explain in words in the box and then click Share with Class. The equation of your best fit line is 0.335x minus 0.057. Looks like I wasn't exactly on the 0 for my y-intercept. I want to use that equation to calculate how high the line will be when x equals 100. My previous estimation was 33, so this stuff here will match whatever data you've been putting in as you work through this. So when I'm plugging in x equals 100, well, again, I'm just going to pop up my calculator here. 0.335 times 100 minus 0.057. And I get 33.43. So again, very similar to the value of 33 that I estimated because I was using that skill of my slope of the line between those points. Type it in, share with the class. Well, now we're going to talk about the idea of a residual. So this was one of our vocab terms from this lesson. And if we were doing the book assignment, it would have you calculate a lot of individual residuals. I want to drag the blue points to plot the residuals. The residual is the difference between the actual value of a data set for an x value and the value of the line predicted for that x value. So for my first residual, x equals 1, it looked like x equals 1 minus 0.3, which was 0.7. Well, now I want to check my other residuals. So to calculate this, my actual value when x is 2, my y value is 3. Well, my predicted y value, if I calculate this out, one sec. Yeah. So I went to check my work and it won't let me undo it. But what I did to plot my residuals here is I had to find my actual value and my predicted value for each of the points that I had, each of those green points. So like the first one was done for me. When I plug in a value of x into my equation, I find out that the predicted y value is 0.278. And now for the purposes of this activity, we're going to be rounding to the nearest tenth each time. So that's where we got this 0.3 value from. So when when x was 1, y was 1. But we predicted that it should have been 0.3. So the residual in this case is 0.7. That's why the blue dot is right here. Well, now the next point that I have is x equals 2. And so using my equation, when I plug in x equals 2, I find a predicted y value of 0.613. But that is different than the actual y value. So I take my actual y value of 3, subtract then my predicted y value of 0.6, and I find a residual of 2.4. Next one, I do the same thing. When x is 5, using my equation, I would predict that my y value is going to be 1.6. So I take my actual value, y is 1, minus the predicted value of 1.6, and I find that my residual is a negative 0.4. This one here, well, I'm expecting my residual to be pretty close to 0 because it looks like that green dot is on the line. And mathematically, when I plug it in, for an x value of 6, y is 1.953, which rounds to 2, and my actual value was 2, so I get a residual of 0. 2 more points, we'll just walk through them real quick. This one here, my actual y value when x is 9, my actual value was 5, my predicted value was 2.958, so my residual is 2. Last one, when x is 10, my predicted y value was 3.3, my actual y value was 2, so 2 minus 3.3 gives me a residual of negative 1.3. So I've got each of mine here, and when you do this on your page, you'll be able to check my work and it'll show you those blue dots moving to the correct spot. So if you did something wrong, it'll still have the correct values for you. Well, now we're going to talk about the square of the residual. And this part here goes a little farther than what your textbook does, but I think it's a really useful way of analyzing the correlation coefficient. So we're going to square each of our residuals and then add them up. And the smaller the r squared value is, the better the line of fit is. So we're going to calculate the square of each residual and enter it into the table. The first one of 0.7 was done for us. So let's calculate our other residuals here. I have 2.4 squared, which gives me 5.76. And I have a negative 0.6 squared, which gives me a negative 0.36. Oops, probably should put a 0 in front of it just for clarity's sake. The square of 0 is 0. The square of 2 is 4. The square of negative 1.3 is 1.69. Calculate the sum. We're going to add up each of those pieces. Oh, one of my values was incorrect. Silly mistake. Negative 0.6 times a negative 0.6 is a positive 0.36. Miss O'Leary makes mistakes too. There we go. The sum of our squares is 12.3. So when I look at this here, maybe not my best work. So let's keep going and see if we can come up with a better line of fit. What we're going to do now is we're going to drag the black points to fit a different line to the points. When you think you have the best fit line, see if any of your classmates has a lower sum of the square of the residuals. So right now, that original line, I have a sum of 12.3. Well, let's drag it around and see if we can get that to be smaller. Oh, that's getting bigger. I can drag either point here. Oh, it's getting smaller. If I take a look at those blue dots there, my residuals are moving, and I want them to be as close to 0 as possible, because when I square values that are close to 0, I'm going to get a final answer close to 0. So let's see, we'll go with that line there. That's a pretty small square of the residuals. I've got 9.06. Right now, it's the smallest in the class because I'm the first person to complete this activity. And which of the purple dots does it intersect? Well, if I look at this now, I can tell that the line of best fit is really going to intersect C. When you're done, I think it saves everything for you. There's no button to hit for submit. But what you're going to do now is you're going to go on to step 2 on the notebook page. These ones here from step 2 and 3, you're going to be writing in your math notebook. You're going to be recording your answers for the homework. This stuff here is all saved on Desmos, but the other one is not going to save to your account. So you're going to need to write down answers on paper. So I'm going to pause the video for a second to get you to the next activity. So to do step 2, you're going to open up this learning activity, learn.desmos.com/regressions, and you're going to take the interactive tour. You can choose to watch the video if you'd like, but I think this is really going to walk you through it step by step. So what you'll do is you'll follow the instructions that it gives you. We're going to head over to Google Docs to copy and paste some sample data. And this sample data tells us about some basketball stuff. What I'm going to do is I'm just going to drag over all of it and Control-C to copy. And I'm going to paste it into the box here. It'll automatically generate a table for me. And I'm going to add a new item. This time I'm going to add an expression. I'm going to add in this line of best fit. So this Y1 approximates the data mx1 plus b. What that tells us is those are our two titles of our data, x1 and y1. It's not the same as we talk about x1 and y1 when we use the slope formula. So when I type y1, I'm going to type the tilde, or that little wiggly line, mx1 plus b. So that's forcing it into the format of a linear equation. So if I look at this here, the residuals are the difference between the data and your model. Click to add them to your table and plot them on the graph. So this time, instead of individually calculating each of the residuals, we're just going to plot them. It's built into our model here. Make my head out of the way. There we go. And we see that we have our residuals. But if I look at my residuals here, I see a pattern. And now if you see a pattern of your residuals, that tells you that there may be a better model to fit your data. If I look back at my original green dots here, it looked non-linear. I want you to know how to plot linear, but this one here, it's going to walk us through the process of finding a better model. What we're going to do is we're going to try the model that looks like a times x1 minus h. We're doing, to do the squared, you press the shift 6 and it gives you that little caret to go up. We are doing a quadratic function here, and then plus b. Now if I look at this here, I see a beautiful curve that matches my data points. My residuals are all bouncing around 0, and there's no longer a pattern, other than the pattern of the fact that they are all very close to 0. If I look at the equation of my line, I can take the data here. But what I want to do is, for my actual steps that I'm going to write in my notebook, I wanted to know about my equation of the line of best fit for my linear approximation. So let's go back. My linear approximation looks like y1 tilde mx1 1 plus b. And in my boxes here, I see my m value, my slope, and my b value. So the equation of my line looks like y equals 0.694, we'll round to the nearest thousandth, x plus 10.228. So the linear approximation of my line is here. The correlation coefficient is that R value, 0.9761. And if I think back to those example R values earlier in this presentation, that's pretty close to 1. That shows us that it's a reasonable pattern of the data. The R squared gets a little more into it. What we care about here is that it's a reasonable approximation. When I add the residuals to the graph, I should notice that these residuals show a pattern, and that tells us that maybe it doesn't quite approximate the data as best it could. And then we followed the steps to find the new model, that quadratic model. So now you're going to practice your skills creating linear regressions with the following sets of data. What we can do is we can just restart within this graph here, or if we go back to Desmos, we can head just to their graphing calculator and it won't pop up with little bubbles at us. When we do our regular calculator here, I can copy and paste my data tables, just like I did for the sample problem. There's an extra A there. I'm not sure that's going to work. Let's see. I paste it. It doesn't paste it as a table. Bummer. I'm going to have to type it in. But that's okay. I can click this plus sign and type in a table, and it gives me that x1, y1. So I can type it in, an x value of 5.7, y value of 3.2, 20, 6.6, 48, 8, 61, and 7.1, 73. Now I want to find the approximation of the data. So again, I do that y1 mx1 plus b. And I can see my data here. Now I'd have to zoom out. There we go. There's my dots. I can see the equation, or I can see my plotted data here. And it's a pretty good approximation. It looks pretty linear. And I can tell from my r squared, or my r value, that it is. It's very close to 1. This data is almost linear. The equation of my line I can write using this information here. And I'm going to let you do the rest of this activity yourself. There's an activity about farming, there's one on sports, and there's one on a student council election. Make sure that you read and answer each of these questions in your notebook, and then I'll post the key sometime tomorrow. If you finish this and you've got some extra time or you want some extra help, you can go back to this learning activity, if you click this here, and you can play with the graphing challenges. What I'm telling you is those graphing challenges are really tough using what you know in the 8th grade. You can probably get the first 2 done, but the other ones after that get to some higher level math. But you can also take a look at the example graphs. These example graphs will show you some different information. If you click around, it'll give you ideas that you can work with. A linear and then 2 nonlinear ones. So poke around, do your best. And then when you're ready, you can finish up your homework. So if I open this up here, there we go. Your homework activity is worksheet 4.6. So it's this activity that's posted on Teams. You're going to do the Desmos activity in Desmos for step 1. And then for step 2 and 3, you're going to be using Desmos as a tool, but you're recording your answers in your notebook. Thanks, guys. Have a great day.